At 60 miles per hour, the steel wheel of a fully loaded freight car supports over 30,000 pounds of pressure. A microscopic loss of lubrication here does not immediately derail a train. It initiates a rapid thermal reaction. The disaster in East Palestine, Ohio, is often characterized as a sudden collision, but the physical evidence tells a different story. This was a progressive, real-time cascade of mechanical, procedural, and communication failures that stacked together over dozens of miles. The National Transportation Safety Board investigation established 3 distinct facts about this incident. First, the physical derailment was triggered by the failure of a single overheated wheel bearing. Second, the multi-million-dollar network of wayside track sensors detected the overheating, but flawed system logic and human workload meant the crew wasn't warned in time to stop the train. Third, the massive chemical burn conducted days after the crash, which released a toxic plume over the region, was later determined by investigators to be entirely unnecessary. Analyzing a complex industrial disaster requires looking past the wreckage. We have to map the systemic blindness that allowed a single failing bearing to destroy an entire train. The roller bearing encases the axle. Lacking federal maintenance requirements, they are rarely inspected. On Train 32N's 23rd car, the L1 bearing lost lubrication. Friction drove internal temperatures past the steel's limits. This extreme burn-off ground the journal into a cone until it completely separated. When the axle severed, it dropped the railcar directly onto the track at milepost 49.5, instantly triggering the train's emergency braking system. The kinetic energy of the heavy freight train forced 38 railcars off the tracks, piling them into a dense, compacted zone of wreckage. While physics dictates how the metal failed, the true breakdown was procedural. The monitoring system meant to catch this failure remained functionally blind until it was too late. This cross-section illustrates how hot box detectors operate. Railroads use infrared track sensors to measure the temperature of wheel bearings against the ambient air as the train passes over them. These sensors only measure the exterior of the bearing cup. If the interior element seize, the external reading can lag 30 to 60 minutes behind the actual thermal event happening inside the axle. 30 miles before the derailment, the train passed a detector in Sebring, Ohio. The sensor recorded a bearing temperature of 38 degrees Fahrenheit above ambient. Because it fell below the programmed threshold, the system triggered 0 alerts. At Salem, the sensor recorded a temperature of 103 degrees above ambient. The system classified this as non-critical. This alert was routed to a remote help desk analyst in Georgia, who was managing a high workload of higher priority alerts. Consequently, the crew in the locomotive was never notified. Local surveillance video captured in Salem at that exact moment showed the wheel bearing was already visibly on fire, contradicting the non-critical data label. Only when the train reached East Palestine did the detector record a severe spike of 253 degrees, finally triggering a critical cab alarm. But by then, the journal had already failed. The industry lacks a centralized database for bearing failures, making it difficult to set more effective detector thresholds. Between the sensor lag, the 20-mile spacing, and the lack of empirical data, the speed of the failure simply outpaced the system. Flammable liquids spilled from the wreckage, igniting a massive trench fire. As local responders arrived, they faced a critical information gap. They had to wait nearly an hour before the railroad transmitted the train's manifest, or consist, detailing the hazardous materials on board. The initial blaze was fueled by legacy DOT 111 tank cars. These older models breached at a rate of roughly 50% upon impact, releasing their contents directly into the fire. 5 intact DOT 105 tank cars carrying vinyl chloride monomer survived the kinetic force of the crash, but they were now trapped in the burning pileup. Responders and on-site contractors feared polymerization, a rapid, self-heating chemical reaction they believed would ultimately lead to a catastrophic explosion. This fear was based on generalized safety pamphlets rather than real-time data. In reality, temperature monitoring showed the tanks were actually stabilizing and cooling. Oxyvinyls, the chemical manufacturer, reviewed the site data and confirmed polymerization was not occurring. However, this expert analysis was siloed and never reached the incident commander. Operating on biased information, contractors gave the incident commander an artificial 13-minute window to authorize an extreme vent and burn procedure. Explosives were used to breach the 5 tanks, igniting the vinyl chloride and sending a toxic plume over the community. The NTSB later ruled this entire procedure was completely unnecessary. The most dangerous element on a hazardous site is an isolated incident command making irreversible decisions based on unverified assumptions. Large-scale disasters occur when multiple independent safety layers fail simultaneously. This is the Swiss cheese model. In East Palestine, 10 specific barriers failed. Barrier 1, the lack of periodic maintenance for freight rail cars. The control is a mandated 5-year comprehensive teardown inspection. Barrier 2, monitoring systems that only read external temperatures. The control is to invest in acoustic or internal predictive sensors. Barrier 3, rigid thresholds that misclassified the early signs of failure. The control is to lower critical thresholds based on actual failure data. Barrier 4, the 20-mile detector gap that delayed the reaction. The control is reducing detector spacing to an average of 15 miles. Barrier 5, the high breach rate of legacy DOT 111 cars. The control is accelerating the phase-out of these models for hazardous service. Barrier 6, the nearly hour-long delay in getting the train's manifest to local responders. The control is real-time, redundant digital manifest sharing. Barrier 7, reliance on generalized safety pamphlets over real-time site data. The control is basing emergency actions strictly on empirical evidence. Barrier 8, siloing the manufacturer's expert analysis. The control is ensuring incident command has unfiltered lines to all subject matter experts. Barrier 9, a remote analyst workload that allowed a warning to go unnoticed. The control is automated cross-checks for high-risk thermal trends. Barrier 10, the lack of a centralized bearing failure database. The control is an industry-wide database to drive better predictive safety algorithms. Correcting just one of these 10 failures could have broken the chain and prevented the disaster. Question 1. In predictive maintenance, what does a rising temperature trend actually signal? It signals impending mechanical failure. It is never a justification for a wait-and-see approach. Questions 2 and 3. True or false? Normal detector readings prove a system is safe. And who must receive verified info during an incident? False. External sensors always lag, and the incident commander must have direct contact with all subject matter experts. Question 4. What is the biggest HazCom mistake? Question 5. Can emergency urgency replace verification? Filtering dissenting expertise is fatal, and unverified assumptions lead to unnecessary catastrophic actions. The professional standard is replacing assumed safe with empirically verified safe. Audit your own systems using this checklist. Review your SOP escalation logic, ensure unfiltered command communication, and trust empirical data over generalities. Which barrier fails first at your workplace? Maintenance, alarms, or communication? Let us know in the comments below. Stay safe.